In this video, we'll continue to look at CSEC Physics past paper questions. We'll be looking at the question from May June 2019, paper 2, question 4. And this question deals with light and optics, right? So May June 2019, paper 2, question 4. Now, the first part of the question, part A1, says, state 3 features of an image produced in a plane mirror, right? So we've all stood in front of a mirror before, and we've all seen an image of ourselves, right? So let's just try to basically jog our memory a bit about what we've seen when you look into a mirror. Now, when you stand in front of a mirror and you look at the image of yourself, one, does your image appear to be larger, smaller, or the same size as you? It appears to be the same size as you, so therefore the image is the same size as the object, right? So the image appears to be the same size as the object. Second question, does the image appear to be further behind the mirror than you are in front? You probably will not be able to, you probably never really pay much attention to that, but the fact of the matter is the image is basically the same equal distance behind the mirror as the object, you, is in front. So the image is the same distance behind the mirror as the object is in front. Also, when you raise your right arm, which arm of the image does it appear to be? When you raise your right arm, it appears to be the left arm of the image. Similarly, when you raise your left arm, it appears to be the right arm of the image. And what this basically means is that the image is laterally inverted. So that's a third property of the image. It is laterally inverted. We could go a little bit further. We know that basically the image is not real. It cannot be projected onto a screen, and therefore the image is virtual. So the question asks for 3 features of an image produced in a plane mirror, and we're able to give 4, right? So that's A, part 1 of the question. Now part 2 says, explain why the word, and it basically has the word police written the wrong way around, is painted in this manner at the front of some emergency vehicles. So let me just write it down. So the word is written as E-C-I-L-O-P, right? So this is how it is written. So they want us to explain why it is written like that on some emergency vehicles. Now, personally, I've never seen the word police written like this on a police vehicle, but of course, I've seen the word ambulance written in a similar fashion. And of course, the reason for that is that when these emergency vehicles are in traffic, they want motorists in front to be able to read these words properly when they are reflected in the rearview mirror, right? So remember, we said that one of the properties of an image produced by a plane mirror is that it is laterally inverted. So in other words then, if you were to write this word the right way around and reflect it in a mirror, it will actually look like this. And therefore, when you write it like this and reflect it in a mirror, it actually looks like it looks the right way around, and so you'll basically have no difficulty figuring out what word it is, right? So for that same reason, the word ambulance is normally written reflected like this, so that upon reflection in the mirror, it appears the right way around, right? So for that reason, those words on emergency vehicles are written like that, due to the fact that, of course, they will be laterally inverted upon reflection, and therefore they will appear to be the right way around and will not pose any difficulty for the for the driver of the vehicle to actually figure out what is on the vehicle. All right. So that is part 2 of that question there. Part B. So part B shows us figure 4 below shows a concave lens. And of course, I'll proceed to drawing a diagram of what is shown, right? I'll try my best, of course, to draw the diagram as best as I possibly can. By now, you should have recognized that my drawing skills are not the best, right? Well, that's not looking bad at all. Well, this is actually a solid line. right? Right, so this line is supposed to pass to the exact center, but it's a little bit off, but we'll just leave it, right? So we have a point here labeled. Let me just make sure about the same distance here. Yeah, label that F. About there. F. All right, so that's basically our diagram, right? So it says, oh, there's a ray of light. There's a ray of light coming parallel toward the principal axis. So this would of course be the principal axis. So, all right, so yes. It says figure 4 below shows a concave lens. Now, clearly, from this, you should be able to identify this as, well, a diverging lens. A concave lens essentially is a diverging lens. So, convex, converging, concave, diverging. So this, of course, is a diverging lens, right? Now, we're seeing a single ray of light coming parallel to the principal axis, and let's see what we're going to be asked to do. It says complete the ray diagram to show the path of the emergent ray after passing through the lens. Now, what do lenses do? Lenses refract, right? So whereas mirrors reflect, lenses refract. And essentially refraction can be said to be the bending of light, which occurs when light passes from one boundary into another, right? Or across a boundary between two media, that is, between two media, right? So basically, this lens will refract the light. Now, because it's a diverging lens and the ray of light is incident parallel to the principal axis, it will be refracted so that it appears to come from the principal focus F. So when we draw our light ray being refracted, we need to basically angle it back and show that it appears to come from the principal focus F. And of course, we're going to use our ruler to do that. Right? So our light ray is going to be refracted, but it appears to come from the principal focus F, and so we extend a broken line back towards F, right? And this line over here, of course, will be solid, right? So let me just extend it a little bit further. Good. So there we have our refracted ray, and it appears to come from the point F. So we notice we used a solid line to represent this because it is a real ray. However, over here we use a broken line because that is imaginary, right? So this ray of light appears to come from F. It does not come from F, and that is why we draw it with a broken line. So you have to remember that when in optics, we use a convention that real is positive, virtual is negative in terms of distances, but also when representing real rays and real objects and so on, we use solid lines, and virtual objects or virtual rays, we use broken lines. Good? So it says complete the ray diagram to show the path of the emerging ray after passing through the lens, and 2 marks for that. And of course, if we did this, we should be able to get our 2 marks, right? So once again, we show the refraction, and it's a diverging lens. So of course, you expect the light ray to spread out, and it also would appear to come from the principal focus F. Good. Label on the diagram the focal length F. So the diagram basically shows the principal foci. Right? The plural of focus is foci, not focuses. So we show 2 principal foci, and by definition, the focal length is a distance from the principal focus to the optical center of the lens. So if we want to basically use a little line, we could basically extend the line through the principal focus, and then the distance through from that line to the line through the optical center, this will be our focal length. So this will be our focal length F, right? Good. An object, so part C. So this is part B of the question. So part C says, an object AB was placed 15 centimeter in front of a converging lens. Now, part C clearly is not related to this part because now we're talking about a converging lens, and this, of course, is a diverging lens. So let's look at part C. An object AB was placed 15 centimeters in front of a converging lens of focal length 5 centimeters. Calculate the image distance. So let's look at part C and write the information that we have. So the object was placed 15 centimeters, which means that basically this is a real object, and therefore the object distance U, so the object distance is equal to plus 15 centimeters, right? Good. Now the focal length of the converging lens is 5 centimeters. So the focal length, F, equals to plus 5 centimeters. Why plus 5? Because once, as I mentioned before, in optics, we use a sign convention, real is positive. A converging lens has a real focus. What exactly does that mean? When light is refracted by a converging lens, the light rays actually meet at the focus. Well, if they're coming parallel to the principal axis, they will actually meet at the principal focus, and therefore because the light rays actually meet at the principal focus is a real focus, and therefore the focal length is positive, right? So of course this is for a converging lens. So it is important then that when we're looking at these questions and we're given the particular lens, we'll always just be given the actual magnitude of the focal length, right? And we are expected to remember that based on the type of lens, the focal length may be positive if it's a converging lens or negative if it's a diverging lens. We might not be given, say, -5 if this was actually a diverging lens, so we need to pay attention to that, right? Good. So now they want us to calculate the image distance, and the image distance, of course, is V. Right? So we're going to be using our lens equation, which is equation 1 over F equals 1 over U plus 1 over V. So because you're interested in finding V, let's make 1 over V the subject. And so we have 1 over V would be equal to 1 over F minus 1 over U. And let's substitute our values and do our calculation, right? So 1 over V is equal to 1 over 5. Now, there's no need to convert these to meters, right? So as long as the units are consistent. So 1 over 5 minus 1 over 15. Of course, you could easily work out these on a calculator, but at this level, you should have no problem when it comes to, adding or subtracting two fractions, right? So the LCM of 5 and 15, that would be 15. 5 into 15 goes 3. 3 ones, that's 3. 15 into 12 goes 1. 1 times 1 is 1. And so we have this is equal to 2 over 15. So we have 1 over V is equal to 2 over 15. And this therefore means that V is equal to 15 over 2. So if 1 over V equals 2 over 15, we reciprocate both sides and we basically find the value of V. And so this will be giving us 7.5 centimeters, right? So 7.5 centimeters will be the image distance, right? Now, one thing worth noting is that the image distance is positive. So whenever we use the lens equation to calculate either F, U, or V, then we need to pay attention to the sign because this has significance, right? And what is the significance of this? Because the image distance is positive, then this basically tells us that the image is real, right? So once again, because the image distance is positive, then this tells us that the image is real. Good? All right, so last part of the question, they want us to find the magnification of the image formed, right? Magnification. Now, when it comes to magnification basically tells us how many times the image is larger than the object, or in other words, then the ratio of the size of the image to the size of the object. So usually for a magnification of 1, it would mean that the image and the object are the same size. If the magnification is greater than 1, then it means that the image is actually larger than the object, so we can say it was enlarged. However, if the magnification is less than 1, it means the image is actually smaller than the object and it was diminished, right? So Let me just make, do I need to make space? No. Let me just do it here. So the magnification M, is equal to the image distance V divided by the object distance U. Now bear in mind, I just said that when you do a question, the image distance may actually work out to be negative. However, whenever we're using it to calculate magnification, we just use the magnitude of the absolute value. So even if the image distance had worked to be minus 7.5, we would still use 7.5 when calculating the magnification. So this gives us 7.5 divided by 15, which is equal to 0.5. So the magnification is 0.5, and which basically tells us that the image is half the size of the object, right? So this was question May June 2019, paper 2 question 4 on light and optics.